So, um, imagine if a single number inside a spacecraft's navigation computer just flips. From +1 to -1. The ship doesn't just drift off course. Mathematically, the flight software suddenly believes the entire spacecraft has been turned inside out into like a mirror universe.
Yeah, the left thruster becomes the
Yeah.
right thruster, up is down. It's instantly catastrophic.
It's
Yeah.
terrifying. And welcome to this deep dive. You are here because, well, as a learner, you want the gears, not just the grease. You want to understand the hidden architecture of the systems all around you.
Right.
So today our mission is to decode this really fascinating stack of notes we have on matrix theory, domains, and code. And we're not just looking at the abstract math of matrices and determinants, but exactly how these mathematical grids secretly govern our physical sky, the electricity in our devices, and even the digital worlds on our screens.
Yeah, it is mind-bending how much of modern reality relies on just, well, finding the inverse of a matrix.
Okay, let's unpack this. Because before we can fly a spacecraft or render a 3D game, we need the rulebook.
Exactly. And to appreciate how those systems work or how they completely fail, we really have to look at the gatekeepers of that matrix, the determinant.
Right.
When you're dealing with invertible matrices, which are basically just square arrays of data representing a transformation, you're constantly asking one question, which is, can I undo what I just did?
So, like, if I apply a transformation to a set of data, can I mathematically walk it backward to its original state? I always think of it like an encryption key.
Oh, that's a good analogy.
Thanks. Yeah, if an inverse exists, you can decrypt the data. If it doesn't, the door just locks behind you.
It's lost forever. And, the way we determine if that key exists is by checking if the matrix is non-singular, meaning its determinant is not 0. So formally, if you have a square matrix A, it has an inverse B if A times B equals B times A equals the identity matrix.
Right, it's the identity matrix.
Yeah. What's fascinating here is how that entire sprawling grid of complex data, which, could be tracking millions of variables, is ultimately judged by a single scalar value.
It's like the DNA or the fingerprint of a matrix. One powerful number.
Exactly. If the determinant is 0, the matrix is singular. The operation cannot be inverted, period. If it's anything else, you can walk it backward.
Okay, but how do we actually find that fingerprint? Because the source material spends like a lot of time on Laplace expansion for computing a determinant, especially for a standard 3x3 grid. And I don't want to just recite an algebra textbook with all the a 1, 1 times a 2, 2 stuff.
Yeah, no one wants that.
Yeah, so what is the actual mechanism happening there?
Conceptually, Laplace expansion is just a process of recursive elimination. You can't easily calculate the scaling factor of a complex multidimensional shape all at once.
Right.
So the algorithm takes the top row of your grid,
Oh.
locks onto the first value, that 1, 1, and essentially crosses out the rest of that row and column. It just ignores them completely.
It zooms in on what's left,
Right.
which is a smaller 2x2 grid.
Yeah.
The notes call that a minor.
Yes, exactly. Isolates that minor, computes its value by cross-multiplying, a 2, 2 times a 3, 3 minus a 2, 3 times a 3, 2, and then it rhythmically moves across the top row.
Just repeating the process.
Right. Zooming in, cross-multiplying, and alternating between subtracting and adding those pieces together. You're systematically slicing a 3-dimensional problem into a series of 2-dimensional planes until you just distill the whole thing down to one core scalar value.
Wow. And that single value is incredibly rigid. The sources outline 4 structural properties that dictate how determinants behave. The one that immediately caught my eye was the all zero or identical property.
Oh, yeah.
Because the notes state that if any 2 rows or columns in your grid match perfectly, or if a whole row is just zeros, the determinant is instantly 0. Why does that happen, like mechanically?
Well, think about what a matrix actually represents, right? Distinct dimensions of data or physical space.
Yeah.
If you have a row of zeros, it means one of your dimensions contains absolutely no information.
So it basically flatlines.
It flatlines. If you have a 3D object and you suddenly declare its depth is 0, the whole thing flattens into a 2D pancake.
Right.
And the 3D volume of a 2D pancake is 0. The determinant measures that volume scaling. The same thing happens if 2 rows are identical.
Because they're redundant.
Exactly. 2 of your dimensions are pointing in the exact same direction. You've lost a dimension of freedom, the space collapses, and boom, the determinant hits 0.
That makes so much sense visually. And it sort of clarifies the other properties too, right? Like the multiplicative one where the determinant of A times B is just their individual determinants multiplied.
Yeah, that one's straightforward.
But the scalar multiplication one is wild. If you scale an entire matrix by a factor of k, The new determinant is k to the power of n times the original.
Which trips a lot of people up. But think about it. If you double the dimensions of a 3D cube, the volume doesn't just double. It increases by a factor of 8, 2 to the power of 3.
Because you doubled the length, the width, and the height.
Exactly. The math perfectly mirrors physical reality.
And that physical reality is a great pivot, actually. Because staring at Laplace expansions on a whiteboard is one thing, but the notes take this directly into the sky.
Yes, into aerospace engineering.
Right. Where engineers rely on direction cosine matrices, or DCMs. These are rotation matrices used to track a spacecraft's orientation.
Navigating in a vacuum is incredibly difficult because, well, there's no fixed ground.
Right, there's no up or down.
Exactly. A spacecraft has its own local perspective called the body frame, and that frame might be tumbling and spinning. But to know where it actually is, the flight software has to constantly map that tumbling body frame back to a fixed global coordinate system, the Earth-centered inertial frame.
And the rotation matrix, we can call it R, is the bridge between those two frames. But reading through this, there is a terrifyingly strict speed limit on that bridge.
Very strict.
For a rotation matrix to be physically valid, its determinant must be exactly positive 1.
Not 1.001, exactly 1.
Right.
Because a determinant of positive 1 guarantees 3 things. It preserves the physical length of the object, it preserves the angles between its parts, and crucially, it preserves handedness. It proves mathematically that the spacecraft hasn't been stretched or distorted by a software calculation.
Wait, so if a software glitch flips a sign and makes the determinant negative 1, the spacecraft mathematically thinks it just mirrored itself inside out into a parallel universe.
Basically, yes. The flight computer will blindly trust the math it's given. A determinant of negative 1 means the coordinate system just flipped from right-handed to left-handed.
Oh, wow.
Imagine trying to put your right glove on your left hand. It doesn't fit unless you turn the glove completely inside out. So if the matrix determinant is negative 1, the software mathematically assumes the spacecraft is inside out.
So if it fires a thruster,
it fires in the exact wrong direction, pushing the craft into an uncontrollable spin. So the determinant acts as this ultimate reality check before any physical hardware is engaged.
That is wild. And to constantly check this reality, the spacecraft has to reverse these transformations thousands of times a second, right? It needs the inverse of the rotation matrix to translate sensor data back to the global frame.
It does.
But wait, we have massive supercomputers now. Why is finding the invert such a bottleneck that it gets its own special section in these nodes?
Because matrix inversion is notoriously expensive in terms of CPU processing. If you're running complex Laplace expansions for every single calculation during, say, atmospheric reentry...
I'll choke the computer.
Exactly. But rotation matrices belong to a special class called orthogonal matrices. The sources highlight a massive computational shortcut here. For an orthogonal matrix, the inverse is simply equal to the transpose.
The transpose, that's just swapping the rows and the columns, right?
Yeah. So instead of running a complex recursive algorithm to find the inverse, the computer just flips the grid diagonally.
Wow, that's all it takes.
That's all it takes. The symmetry of an orthogonal matrix means you bypass the heavy lifting entirely. It turns an operation that could lag a flight computer into something that executes almost instantaneously. That shortcut is literally life and death for real-time flight control.
That is so cool. Okay, so moving from the macroscopic scale of a spacecraft down to the microscopic scale. The notes show how this identical mathematical framework controls movement we can't even see, like the flow of electricity across a circuit board.
Right. Electronics engineering relies on a completely different physical medium, but the structural math is exactly the same.
Yeah. When engineers design complex electrical networks, they use linear circuit simulation software, things like SPICE, to model the behavior before anything is manufactured. They use nodal analysis based on Kirchhoff's current law.
Yes, and the fundamental equation there is Y times V equals I.
Where I is the source current, the power coming in, and V represents the unknown node voltages they want to find.
Right, but Y is the fascinating part here. That's the nodal admittance matrix. Y essentially represents conductivity. It maps out how easily current can flow between every single node in the network, factoring in all the resistors, the capacitors, the pathways.
Here's where it gets really interesting, at least for me. Because I found myself thinking of it like a massive, complex plumbing system. The voltage, V, is the water pressure at various points.
Wow.
The current, I, is the actual volume of water flowing through. And that admittance matrix, Y, is the physical layout of the pipes. The notes state that if the determinant of y is 0, the circuit is singular. What does a singular pipe layout look like?
Well, keeping with your analogy, it looks like a system with water being pumped in, but absolutely nowhere for it to go. Like a pipe layout with no drain, or maybe a closed loop that's completely disconnected from the main water supply. In electrical terms, if the determinant of y is 0, the circuit might be ungrounded, or a segment might be floating with no reference to ground.
Right. And without a drain, you can't calculate the water pressure. The math breaks down. To find the exact voltage distribution, so solving for VBDS, the simulation software has to compute the inverse of y and multiply it by the current,
Which brings us right back to our gatekeeper.
the determinant.
If we connect this to the bigger picture, if the determinant of y is 0, that inverse does not exist. The system of equations has no unique solution.
The software throws an error.
Exactly, because the math is warning you that the physical circuit you just designed is unrealizable. Modern electronics rely entirely on the software's ability to find that inverse to guarantee a steady-state solution.
Before a single physical wire is actually soldered.
Precisely. It saves millions of dollars in manufacturing.
So we have physical space in aerospace and electrical flow in hardware engineering. Both systems are bound by the strict rules of physics. A 0 or a negative determinant represents a catastrophic failure. But the third domain in our sources takes us into computing and computer science, specifically 3D computer graphics. And here, the rules of physics are, well, totally optional.
Digital rendering pipelines are fascinating for exactly that reason. You are constantly manipulating artificial geometry. Game engines and computer vision frameworks rely on affine transformations matrices that scale, rotate, translate, and ultimately project 3D models onto your flat 2D screen.
And in this domain, the determinant represents the volumetric scaling factor. Like, if the determinant is greater than 1, the digital asset expands. If it's between 0 and 1, it shrinks.
Yeah.
But the notes highlight what happens when the determinant drops below 0. In a spacecraft, that was our mirror universe death spiral. But in a 3D game engine, a negative determinant is actually a feature, not a bug. It triggers something called backface culling.
Right, so consider how a 3D environment is built. Everything is made of polygons, mostly triangles, and those triangles have a specific winding order, the sequence in which their corners or vertices are drawn. That winding order determines which side of the triangle is the front and which is the back.
So, if I have a character in a game, and they turn around and walk away from me, my camera is now looking at the back of their head. The geometry of their face is still there in the world. It's just pointing away from me.
Right, and drawing that face requires a massive amount of processing power. You're calculating textures, lighting, shadows. The rendering engine needs a really fast mathematical way to know if a polygon is facing the camera or facing away.
Because if it's facing away, why draw it?
Exactly. When a polygon is pointing away from the camera's perspective, the determinant of its transformation matrix effectively becomes negative relative to the view space. The geometry is geometrically inverted from the camera's point of view.
So the math acts like a digital director yelling cut on drawing the front of the character.
Pretty much.
It sees the negative determinant, reverses the vertex winding order, and instantly knows it can safely cull or drop that geometry from the rendering queue.
And it saves an unbelievable amount of computational overhead. The computer only draws the surfaces pointing towards you, entirely driven by checking the sign of that determinant.
So cool.
Yeah.
But the rendering pipeline also has to work in reverse, right? Because when I'm playing a game and I click my mouse on the specific pixel on my 2D monitor, the game has to figure out what 3D object I just clicked on.
Right.
The notes call this unprojection. Wait, so every time I click on a character in a 3D game, the engine under the hood is literally inverting a massive matrix just to figure out where my 2D mouse click actually landed in its 3D world.
Every single time, projecting a 3D world onto a 2D screen is relatively straightforward. You're just squashing a dimension.
Okay.
But unprojection, taking a flat 2D click and casting a mathematical ray back into a 3D scene to calculate depth and collision is incredibly complex. Ray tracing algorithms and physics engines do this by computing the exact inverse of the view projection matrix.
And just like the circuit board, that inverse is only possible if the transformation matrix is non-singular.
Yeah. Thousands of times a second, every time you move a mouse, every time a ray traced shadow is cast from a virtual sun, the engine is relying on that matrix being invertible. If it loses that ability, the connection between the 2D interface and the 3D world is completely severed.
Wow. That spans such an incredible breadth of modern technology.
Yeah.
But there is a final section in these notes that addresses how we actually implement this. The theory is elegant, but proving it works on a machine requires writing code.
Yes, the script.
Right. The source material provides a script to construct a standalone verification engine in Python. It manually computes a 3 by 3 determinant using that Laplace expansion we talked about at the beginning, and then it validates that manual calculation against NumPy.
Right, with NumPy being the highly optimized linear algebra library that is basically the industry standard for Python development.
Exactly. So what does this all mean? Reading this, I found myself pushing back a bit. NumPy is backed by a massive open source community. Millions of developers test it every day. Isn't writing your own manual script to compute determinants just begging for human error?
Wow.
I mean, writing a manual verification engine feels like learning to drive a manual transmission before getting an automatic. It proves you understand the gears, sure, but why advocate for reinventing the wheel when you have a perfectly good, highly optimized black box library ready to go?
This raises an important question about trusting black box software, and it's the exact trap a lot of developers fall into.
Really?
Oh, absolutely. When you are programming flight software for an aerospace firm or designing the simulation logic for a high-voltage circuit board, the stakes are just too high to blindly trust a prepackaged library without deeply understanding the mechanics underneath it.
So it's not about replacing NumPy in your production code.
No, it's about structural comprehension. Writing a manual verification engine forces the programmer to confront the edge cases, like what happens to the Laplace expansion when a floating point number gets infinitely close to zero but doesn't quite hit it?
Oh, right, rounding errors.
Exactly. How does the code handle rounding errors in an ill-conditioned matrix? If you don't build the algorithm from scratch at least once, you treat the math like magic. And when the math behaves unexpectedly during a simulation, you won't know how to debug it.
Because you don't know how the gears mesh. You have to know that before you trust an automated system to drive the car.
It creates a foundation of absolute certainty. You manually verify the behavior of the matrix structure, you validate your understanding against the optimized library, and only then do you trust that library to calculate the orbital mechanics of a satellite.
Man, it is a phenomenal journey, taking these abstract algebraic symbols on a page and tracing them out into the real world. We've seen how Laplace expansions and inverses form the invisible rulebook for basically reality.
Yeah, they really do.
The determinant acts as the ultimate logic gate. It verifies the integrity of physical space in aerospace, it guarantees the flow of electricity in hardware simulation, and it selectively builds and destroys digital geometry in rendering engines.
It all comes down to a deterministic view of systems. In classical linear algebra, a state is either invertible or it isn't.
Right.
A system is either physically possible or it is mathematically singular. There is no gray area.
Which brings up a really fascinating thought to leave you with. Everything we've covered today relies entirely on deterministic matrix inversion, right? Where a matrix represents a single transformation yielding one exact scaling factor. But what happens to this entire mathematical foundation when we introduce quantum computing?
Oh man, that is where the ground really drops out from under you.
Right. Classical computing relies on definitive states, but quantum states exist in superposition.
Right, where states exist in multiple conditions simultaneously.
So if a quantum matrix represents multiple overlapping physical realities at once, how does the concept of a determinant even survive? What happens to our scalar fingerprint when a matrix isn't just scaling space by one fixed amount, but potentially expanding, collapsing across probabilities at the exact same time?
It's wild to think about. It forces us to entirely rethink what it means to undo an operation. In a probabilistic system, inverting a transformation might not return you to your exact starting point. It might return you to a whole distribution of possible starting points.
Does the concept of an inverse break down completely? Or does it evolve into a completely new kind of multi-dimensional key?
It definitely challenges every single structural rule we just laid out today.
The invisible rulebook is currently being rewritten. It's definitely something for you to mull over the next time you look up at a plane or boot up a video game, or even wonder how that tiny processor in your pocket actually works. The math never stops evolving. Thank you so much for joining us on this deep dive. Keep asking those questions, keep looking for the gears under the hood, and we will see you next time.